Welcome to the last lecture of Chapter 4. Today's lecture would be very practical. Specifically, we're talking about pe-pH diagram. What we're doing in this lecture would be deriving equations for constructing the diagram itself, and then making it a little bit more complex, and then eventually try to interpret data from that sort of diagram, which is basically talking about dominant species. We're going to solve 3 examples in this lecture, but you see more in problem set and also in the problem solving lecture. So here we're going to do some of the basic calculation and also constructing some of the basic figures. This lecture would be very important. So first, let's talk about why we need pe-pH diagram. What's the problem with just the speciation diagram we had before? Because basically so far we had always speciation, PC versus pH or PC versus PE, what we had in the previous lecture. So that's basically a kind of speciation. So it talks about concentration of one species, so the actual value of the concentration as a function of a parameter. So in this case, for example, PE. But when we look at these lines, we see that this looks like a binary information. For example, look at Cl minus. We have a lot of Cl, we don't have it, roughly. Or the concentration goes from roughly 10 to the minus 3, immediately 10 to the minus 8, so negligible. The same thing for almost all of them, Fe3+, the same thing. We have it or we don't have it. And this was for a specific pH, as you saw in the previous example. So this was, for example, at pH of 7. So now we have the opportunity to repurpose the interpretation from a graph to be not the exact value we're getting, like a PC-PE diagram, but rather the dominant species at a condition. And now because we have that dominant species, we're flexible to add one more label to the y-axis. So this might be a little bit confusing, but here I'm telling, for example, just for the PE, considering the PE as the x-axis, I have either this species or I don't have it. So one layer of information. But now I can do the same thing for different pH. So this might be a little bit different. So I'm talking about the zone within that 2D diagram of pH-PE. So this would be more clear, but just keep in mind the type of diagram we're talking about today. It's not talking about the exact species concentration, but rather what species is the dominant in that region of pH-PE. Again, it's a very important information to predict what you're expecting in that region. So this would be the whole idea of the pe-pH diagram. So rather than the concentration, the exact concentration, we talk about the dominant species. So the concentration, obviously, it's not shown here in those graphs, but rather it's just basically what is dominant. So if you remember from the PC-pH or PC-PE, we're eventually talking about an equation for the line, or an equation that is either pH dependent or PE dependent. And then we take it to Excel, construct every single line. But here it would be a little bit simpler in terms of driving that equation. So we're looking for an equation that has an expression of either pH or PE or both. So this would be what we're looking for. So keeping that in mind, we're going to construct basically different equations for different lines. So here we start from the simplest. As I mentioned, this has a lot of similarity to the Porbay diagram, which is extremely useful and is extremely important. And here is basically pretty much the same as the Porbay diagram. So what we're including is redox reaction, acid-base reaction, and a complexation reaction also. So to include all of them in the pe-pH diagram. So as you know, this is sort of water chemistry. So everything is contained within the body of water. So when it comes to oxidation and reduction, something that we have to always consider is water oxidation and water reduction. And if you're taking electrochemistry class, going beyond that is not feasible because you're limited by these 2 reactions. So basically that's why we're including these 2 reactions. So this is something that we always have it in our pe-pH diagram, as long as obviously we're in a water system, which is the case for almost all the equations we have here. So now we want to see if we can have a line representing this information in a pH or a pe-pH diagram. And that means we have to somehow work with the equilibrium expression to have an equation of a line that is sort of something like this, A pH plus B. So something like that. So now we want to see how we can do that. What is given here is the K value. So it's just an expression of the equilibrium. We can basically use that expression to write the equilibrium. So K would be the product, in this case, water to the power of 2, and then oxygen, because in the gas form, we basically talk about the partial pressure. And then the electron as a species to the power of 4. So this is just a typical expression for the equilibrium. So the next part would be, so one specific information is that on the line, we're talking about equilibrium of the two species, and the same ratio happens on the line. So we'll use that information later. So, a second. So to a little bit simplify this, we're working with, so the activity of water, we're considering that to be 1. And also we're assuming a standard condition, so the partial pressure of oxygen would be 1. So this relationship would be K equal to 1 over H plus to the power of 4, and then E to the power of 4. So we're interested to work with PE and pH. So a little bit of playing with the log function. So log of both sides would be log of K. Then this would be minus log of H plus to the power of 4 plus log of electron to the power of 4. Or this would be 4 minus log of H plus minus log of electron. As you know, this would be basically the pH, and this would be PE. So then we can basically say log of K would be 4 pH plus PE, and then considering the log of K to be equal to 83.1, then we get to this line, PE equal to 20.8 minus the pH. So again, what we did was pretty straightforward. We used the expression of the equilibrium. We wrote it in a way that eventually gives us PE and pH. And then we have an equation as a function of PE and pH, because that's basically the space we're interested in, to predict, to give us a line that in that line, we have equilibrium between the species. So now this will be more clear as we proceed, but for now we're interested to know about that exact equation of the line. Since we have water oxidation, we also have water reduction, and the equation for water reduction would be this one with this log value. We can do the same thing here. So the equilibrium of the expression. K would be the partial pressure of hydrogen, hydroxide, and then water and then electron. So this would be 1, this would be again 1, and then eventually would give us K equal to hydrogen hydroxide and then electron. And because we're interested to know about pH, we can basically convert that OH minus to H plus. So this would be KW over H plus to the power of 2, and then divided by the electron to the power of 2. The same thing if we do log. What we get is basically log of K equal to 2 log of KW minus 2 log of H plus minus 2 log of electron. So obviously this would be 2 pH. This would be 2 PE. Then we can rearrange it. PE equal to log of K minus 2 log of KW, then minus 2 pH divided by 2. What's the PE then? Exactly. So this one is minus 28 given. KW is 10 to the minus 14. So if we do this part would be 28. So it would cancel these two. And then eventually 2 goes by 2. And then we eventually get minus the pH. And that's the second line. And this line is very similar to the H plus and OH minus line in PCPH. We always had that 2 line, always. And this is basically the case here in a pe-pH diagram. You're always limited by that water splitting window. So to make it more technical and using that sort of electrochemistry language. So the next part is we have these 2 lines. We can just basically construct it in a pe-pH diagram. The first one is, what is the value? 20.8 minus pH. So we just need 2 points. Let's say the pH of 0. Then that would be 20.8. So roughly here. And then the other one, let's say we have a pH of 10. Then it would be 10.8, right? So it would be roughly, so this is 10 and 10.8. So I lost it. Okay, so that's the 2 line. Okay, so this line represents the first reaction, or this line represents water oxidation. So a few important information about the line itself. So we have the expression of the line in terms of mathematical expression. But what is the physical meaning of the line itself? Like, what are the concentrations of each, or the ratio of the concentration on the line? So it's basically the equal concentration on both, on the line of the reactant versus the product. So we're going to use that later. So it seems one side of the line, one of the species is dominant, either the reactant or the product, and the other side, the other one is dominant. So that's basically the whole purpose of this. We are dividing the whole area into two zones using this line. A zone that one species is dominant, and the other zone that the other species is dominant. And on the line is basically that equilibrium, the same ratio. So when we look at the reaction, it's basically the game between water and oxygen, because these two are basically how we can manipulate it. So to identify whether this zone is oxygen or water, how we can proceed? So obviously this side has lower electron activity compared to this side, right? So lower the electron activity, it favors the forward reaction or the backward? So you have lower of this guy. So it favors this reaction. So in that region, the dominant species is oxygen. So basically this is the region that oxygen is dominant. So this line, this side of the line, basically oxygen. Obviously this side is the other one. Or more electron, more reduced species is dominant. So if I ask you, for example, at pH of 8 and PE of 0, the dominant species would be water. If you want to have more oxygen, then you just continue with reducing the PE, keeping the same pH. So again, the information on the line is basically the same ratio. Either side of the line is basically one of the species is dominant. That's the whole purpose of this graph. We're basically defining zone. So far, we defined two zones: oxygen zone, water zone. So the other one is, the other relationship for the other reaction is PE is equal to minus pH. So again, 2.0 would be on 0. And then let's say 10 would be on 10. So there's two lines. If we have this 2 point, obviously parallel, both of them minus pH is the minus 1 is the slope. So this is water reduction. So just freezing on the green zone, green line, ignoring the blue line. The green line is dividing this area into two parts. One part and then two parts. Just the green line. What is this zone, like the top zone, based on the green line? Less activity of electron. What is it on the top? So it would be water. And then the bottom would be hydrogen, right? So it seems we have three regions: the hydrogen region, the water region, and then the oxygen region. So whatever that could happen, redox, acid, base, anything in terms of the speciation, must happen in this window. So this is basically the water window. Otherwise, beyond that, this would be oxygen dominant, this would be hydrogen dominant. So that would be basically the window, the operational window for our pe-pH diagram, because if we pass that, then the dominant reaction would be related to water, not those species that we have. So far what we did was drawing the line. The other thing was distinguishing what is on this side of the line, the other side of the line. And each zone would give us what is dominant. But really, it doesn't matter between these 2 points or these 4 points. All of them, water is dominant. And we don't know what's the concentration of water or what's the concentration of, for example, hydrogen or oxygen here, because we don't care about that. It's just the dominant species, that kind of information. So now we want to expand this for a more complex system. It seems we're dealing with a PE equal to A pH plus B kind of expression. B could be 0, A could be 0, depending on the system, but it seems it's sort of a linear trend with this expression. So we're expecting that sort of thing. And now we want to use this and solve it for different systems, and then eventually put every line into the graph. So let's focus first on some simplified version. For example, on a system that has only electron transfer and no proton transfer. So let's see what's the line. So this is given, and the PE value is given. Obviously, this is not the standard reaction, so we have to first make it standard. It would be on the oxidation formation, releasing 1 electron. And now we could use E0 as the expression of this new standard reaction. And minus log, this would be PE0 equal to minus log of Fe3 plus Fe2 plus PE. How can we further simplify this? So we're not interested to look at all the concentration, because the equation of the line is representing only one condition, that line itself. And that one condition is basically we have the equal amount of the reduced species and the oxidized species. So that's basically what happens on the line. So then this would be 1. Obviously, this would be all equal to 0. Therefore, what we're getting is basically PE equal to PE0, which is basically a horizontal line. In this case, this is 13.303. So for a simple redox reaction with no proton involved, what we're getting is a horizontal line. So you'll see some of the examples later. And the reason is basically this one, because eventually if we rearrange the equilibrium expression, we would get to that. Similarly, if we have just an acid-base reaction, it would be a vertical line. And it makes sense. This reaction is not pH dependent. So across any pH, this would be the same profile. So obviously the same thing for here. This is not electron activity dependent. So at any electron activity, it should be the same. So it's basically just pH dependent. And if we actually derive that, this would be Ka1 HCO3 minus H plus and carbonic acid minus log And assuming that the ratio are the same, the ratio is 1, so the concentrations are the same, eventually we would get to this relationship. Or like opposite, pH is equal to pKa. In this case, 6.3. So this would be a vertical line. But as you know, this might be a little bit more complex, involving a redox reaction that has electron and proton. Then we don't have a vertical or horizontal line, but rather we have a line that has some slope. You saw that right here. So this is basically a reaction that involves both proton and electron, both of them. That's why this is basically a tilted line. This would be if a reaction is basically just acid base, this would be a reaction that has just a simple redox reaction. So 3 types of lines we'll get, and you'll see. So this was very specific case. Now we want to make it basically having a general rule of how to construct a pe-pH kind of diagram. So the first time when we read this, this might not be very self-explanatory, but when we solve 3 examples, it would be more clear. The first step is make a species list. This is either given or we know how to do that, how to identify what species we have based on what we've learned before. Then we look at look at the oxidation state to identify how these species are related. Again, this might not be clear, you'll see that soon. And then consider what kind of chemical reactions we should use. Then list all the equilibrium expression. Then talking about the equation of the line. So this would be basically step 4. Then plot the line. Then this would be a pretty easy task. But this part 6, is probably the trickiest part, is to erase a part of the line that is thermodynamically impossible. So this is, I know this is very vague, but we will see that through the examples, how we erase some parts of the line. So this could be a complex task, but we try to make it simplified. So what we do is basically we have a line, but some part of the line, it doesn't make sense. So now we want to identify what part of the line doesn't make sense through the example. So the first example 1, what we're doing is just to construct the equation of the line. So we're doing up to part 4. So we're not plotting it and we're not erasing the part that doesn't make sense. But in example 2 and 3, we're going to do all of it. So the first part is just a quick practice to practice the first 4 steps. So now we have a system that is a nitrogen-based species. We have ammonia, we have ammonium, we have nitrate, and nitrate. So 4 species are given, right? And just let's say we don't have this information. Let's just ignore it for now. We need to first evaluate what kind of possible reactions we might have between the species. And if you remember at the very first lecture of chapter 4, I talked about the oxidation state. For any redox reaction, the oxidation state would change. So the first thing is to look at the oxidation state of nitrogen in all the 4 molecules. And if it's different, we have at least a redox reaction associating between the 2. So let's look at the species. We have ammonia, we have ammonium, we have nitrate and nitrate. And we want to look at the oxidation state of nitrogen. What is it in ammonia? -3, okay. In ammonium, minus 3. So before we proceed, are we expecting a redox reaction that in one hand involves ammonia and the other hand ammonium? No, because the oxidation state didn't change. But the number of proton changed, so we're expecting an acid-base reaction between the two. So what is it in nitrate? Plus 5. And nitrite? Exactly. So how many reactions we're expecting, or how many lines we're expecting eventually? Someone said 4. No? Okay, so this was. So I go with the simplest. We're expecting an acid-base reaction between ammonium and ammonia. What else? So a redox reaction between these two because the oxidation state would change. So what else? The species are there in the system. We don't have any control on the kind of reaction that might be involved in. Why not ammonia and nitrate? They could, because minus 3 and 5. How about ammonia and nitrate? It could. Ammonium and nitrate, the same logic, and ammonium and nitrate. So how many we got? Overall, how many reactions? 6 reactions. So there are 6 different reactions that could involve this species. Out of 6, how many redox? 5. 1 redox only? What's that? 5 redox. 1 acid base. So the only acid base is between the two that doesn't change, that there's no change in the oxidation state. So now we want to do, so what we did was basically the first few steps. And now we want to do step 3, list all equilibrium expression for what we identify. And then later, just rearrange it in a way that it's a pe-pH. So we're doing up to part 4. So the next part would be reactions. So reactions. The first reaction is acid base, ammonium going to ammonia plus H plus. So this would be pKa. And what we've learned in the previous page, this would be the line representing this one would be pH equal to pKa equal to 9.25. And you can see also here all the constants are given, and when you look at the subscript, you see that ammonia nitrate, ammonium nitrate, ammonium nitrite, and you see all the pairs here basically. So that's sort of, it gives us all the possibilities. So this is the first line. It's a very simple line, a vertical line that is representing this reaction, obviously an acid-base reaction. So now let's focus on the second line. Let's say we go with this order. So this would be this line. So this would be ammonia and nitrate. So ammonia. On the other side, we have nitrate. I'm not going to go through the balancing this reaction. We covered that before. So this would be 3H2O. On this side, 9 proton plus 8 electron. We don't have any information about this reaction because this is not a standard reaction. The K values are not given, rather E0 values are given. So we need to convert this into the standard format. So releasing 1 electron plus 3/8 H2O, then forming 1/8 of nitrate, 9/8 of proton, and then electron. And now this is a reaction that we could work with, basically using that E0 value, the corresponding E0 value. So the K for this reaction would be E0 of ammonia and nitrate. Would be to the power of 1/8 H plus electron and then the reactant. I'm also including water, but as you know, this is basically the activity of water is 1. So the next part would be minus log of both sides to get to that form of pe-pH kind of thing. And if we do that, then it would be P0 minus 1/8 log of nitrate plus 9/8 of proton of pH plus PE. And then as we know, on the line, this is the ratio bond. So this part would be equal to 0. So what we get is PE equal to 13.73 minus 9/8 of pH. This 13.73 is obviously PE0 corresponding to this reaction. So this would be the second line. So we continue with the rest of the redox reaction. The next one that is given, let's just keep the order. It would be ammonia and nitrate, then ammonium and nitrate, then ammonium and nitrate, and so on. So the third one would be ammonium and nitrate. Again, balancing this reaction would be something like this. This is not the type of reaction we could work with, so we need to make it standard. 1/8 of ammonium, 3/8 of water, 1/8 of nitrate, plus 5/4 of proton, and then 1 electron. So I'm not going to go through the K expression. It would be the same as the previous case. Then here would be, again, the same, simplifying this one. Eventually, if we do this, it would be PE equal to PE0 minus 5/4 of pH. And when we implement that PE0 value, then it would be PE equal to 14.88 minus 5/4 of pH. So the third line, the fourth line would be between ammonium and nitrate. So This would be ammonium and nitrate, and then 8 proton plus 6 electron. I'm going to skip 2 steps now, so then it would be eventually P equal to P0 minus 4/3 pH, PE equal to 15.08 minus 4/3 of pH. And the fifth one between ammonia and nitrate. Would be eventually PE equal to P0 minus 7.6 of pH, 13.54 minus 7.6 of pH. And the last one is basically between nitrite and nitrate. 2 minus plus water, nitrate plus 2 proton plus 2 electron. Eventually it would be PE, what's the value? 14.29. P0 minus pH, or PE equal to 14.29 minus pH. So what we did was up to, basically we identified all the species it was given. Then we consider which chemical reaction should be used by looking at the oxidation state and then the difference between the oxidation states. Then we list all the equilibrium, and then we write the expression for pe-pH using the equilibrium constant that was given. In this case, it was PE0 that was given, so we had to change the expression of the reaction in the standard notation to be able to use that easier. So the next step would be, obviously, you go to an Excel file, and then based on the line equation of the line, it would be pretty simple. You give it two points, and then you have different lines. So that would be part 5, and then part 6 would be erasing it. We're not doing it for this example, but we'll be doing the full cycle for the following 2 examples. Any question on this part? Pretty straightforward, just coming up with the equation of the line. So that's basically the part that on one side you have one dominant, on the other side the other one dominant. So the point between the 2 is basically the part that you have equal concentration of the 2. When you stay away from the line, one is the dominant. So we again, we don't get the exact concentration from this kind of graph. It's just basically what is dominant. Yeah, that's a good question. So the second example is, in terms of the species, is a little bit simpler. We have Hg2+, we have HgOH2, and then Hg liquid, mercury basically. So first, before looking at the constants that are given, let's see what kind of reaction we have. So in terms of species, we get Hg2 plus HgOH2. Again, this is a dissolved species. This is not a precipitate. And we get Hg in the form of liquid. And one simple thing is to do oxidation state of Hg to see what kind of potential reaction we might have. What is it for Hg2 plus? I mean, 2 plus 2. What is it for HgOH2? Plus 2 again. So, and the last one? 0. So, how many reactions we have and what kind of reaction? How many? 3? Okay. So, one reaction between these two, the same oxidation. So, what kind of reaction is it? Complexation. Complexation reaction. So obviously these two and these two have different oxidation states, so two kind of redox reaction. So now let's do the reactions and the corresponding lines. So the first one, Hg in the form of liquid and Hg2 plus. And if we do the math, to balance the reaction, it would be 2 electrons on this side. Standard reaction would be half of Hg in the form of liquid, half Hg2 plus electron. Eventually, again, I'm skipping the part that I'm writing the expression for K. Eventually would be Pe equal to Pe0. And this would be 14.47. As we were expecting, this is a typical redox reaction, so this is a horizontal line. So the second reaction is between Hg and HgOH2. When we balance this reaction, it would be 2 water here and 2 proton plus 2 electron. We could balance this one or make it standard. And then eventually this would be P equal to P0 minus pH, or P equal to 17.5 minus pH. That line represents this reaction. So the last line is just the complexation between Hg2 plus and HgOH2. So it would be Hg2 plus 2 hydroxide to form HgOH2. And the designation that represent this reaction is beta 2 of hydroxide, and that's basically what is given. So we don't need to rearrange this reaction. We can use it as it is. So this time we need to do a little bit of expression of beta. So beta 2 of hydroxide would be HgOH2, and then Hg2 plus hydroxide to the power of 2, and then we do log of beta would be log HgOH2, Hg2 plus, minus 2 log of OH. So again, this would be 1, this would be 0. Then eventually we get log of beta 2 OH to be equal to minus 2. We convert that OH to log of Kw over H plus. So we're interested to go with pH. Or minus 2 log of Kw plus pH. What's the expression now? Based on the values that are given? Minus or 3.1, right? So this would be minus 14, was 3.1, okay. So then this would be basically pH equal to 3.1. So the reason we drive this expression because this was not pretty straightforward like acid base. So we had to really calculate and then get to this value. It wasn't just simple pKa like what we had before. So now we have the equation for 3 lines. The next part would be to draw those lines using, for example, 2 points. So step 5, and then the next part we do step 6. Okay, let's color code them so it would be easier for drawing. So line 2 would be so now the first line, it would be, what kind of line is it? It's the simple horizontal line. What's the value? 14.47. So roughly here. So this is the very first line. So line number 1. So this line represents the equilibrium between Hg liquid and Hg2 plus. What side is Hg2 plus and what side is Hg? So more electron here, less here. Why liquid? So you have more electron in the bottom. So the top, you get Hg2 plus. Why? You have less electron here. Because it's Pe, so higher the value. less the absolute value of the electron. So more of the electron activity here, so that means it's pushing more of the Hg2 plus to be in the form of Hg. So we get more of Hg liquid here and Hg2 plus here. Because eventually we got Hg2 plus 2 electron to form Hg. So more of the electron goes more Hg. So more of the electron, more of Hg. Just this might be a little bit confusing, This Pe, so lower the value, higher the absolute E value. So that's first line is dividing the whole region into two parts. The Hg2 plus dominant part, the Hg liquid dominant part. So let's go with line 3. I think it's simpler. What is it, this line? Just a simple vertical line at what pH? 3.1. So roughly this is the line. So that's not 2. This is basically line 3. So this is going between Hg2 plus and HgOH2. So when we look at the reaction, more hydroxide, that means more of HgOH2. So just looking at the green line, it divides into two parts. The more hydroxide part, or the higher pH, and the lower hydroxide part. So what is this side? Exactly. So this would be HgOH2. And then this part would be Hg2 plus. So now looking at the last line is line number 2, which is sort of a tilted line with an equation of 17.5 minus pH. The easiest point is pH of 0 and then pH of 14. So that's the two points we can pick. pH of 0, then it would be 17.5, so roughly here. And then the other point, if we pick so this would for sure pass that line. So you can actually put 3.1 and see this would give you the other line so that they will cross. So this is line number 2. So again, try to focus only on the orange line and ignore the other two lines. The orange line is dividing the whole region into two parts. So this is the first part, and this is the second part. So generally speaking, this region has lower electron activity than this region. So lower electron activity, which is this region, it favors what species for this reaction? Or to say more electron activity, that means it pushed the reaction this way. So in the more electron activity, which species is dominant? Exactly. So this means this region is Hg. Once we know one of them, the second one would be easier. Hg and then HgOH2. So we did also part 5. But this is still not a Pourbaix diagram because the kind of diagram we're looking for that tells me in each region, what's the dominant species. So right now we have three independent lines. They're not connected together. It's not telling one story. It's three different stories. The story of the green line is Hg2 plus here dominant, HgOH2 dominant here. So it is not combined together. So that's basically the last step that I was talking about here. Now we did up to part 5. So we need to erase line segments that are thermodynamically impossible. To do so, determine PE and pH values where acid-base and redox transitions occur. Very vague, I know, but we're going to do it on the map itself. So the whole purpose is we have distinguished zone in this plot with connecting the information from all the three lines. So let's focus on line 3. So line 3 is telling me Hg2 plus dominant here, HgOH2 dominant here, right? And let's take that as a reference. So by taking that as a reference, let's focus on line number 1. Line number 1 is going into this region, also this region. The regions are divided by line 3. So line 3 is saying this is a region, the territory of HgOH2. But this line is also here. This line is the equilibrium between Hg2 plus and Hg liquid. But this is the territory of this guy. These two don't belong to this part, right? Because HgOH2 is not there, is not in the reaction. So this part of the line is not thermodynamically feasible because we don't have that reagent. It's not that the dominant based on the three lines because it has to check all the boxes. But how about this part? This is the part that any kind of reaction related to Hg2 plus could happen because it doesn't contradict this information. And this purple line, this part, is talking about these two. So it makes sense that this part is the part that is meaningful. So what we did was just taking 3 as a reference, and then we could do the same thing for other references. I'm taking 3 because it's simpler. So we cut it, we remove the part of the line number 1 that doesn't make sense. So the part that makes sense is basically this part. So that's the first line. So we did the trimming on line number 1. So again, let's use line 3 to trim line 2. Again, this is the territory of HgOH2, and this is the territory of Hg2+. This orange line is passing through both territories. And this line, starting from here, any reaction that doesn't involve Hg2+ doesn't make sense. And this line is only representing Hg liquid and HgOH2. So obviously, this part of the line doesn't make sense, right? How about this part? It does make sense. It doesn't contradict any information. This is the part that HgOH2, and then HgOH2 is involved in the reaction. It's going back and forth between Hg and HgOH2. So we can basically take this part. So we trimmed line number 2 also. Okay, I guess it's time to revenge for the other 2 lines to cut line 3 also. So we can take line 1 as the reference to trim line 3. So line number 1 is dividing the region between Hg2 plus and Hg liquid. So this part is Hg liquid. This reaction doesn't involve any Hg liquid, so it's not valid in the Hg liquid part region based on taking line 1 as a reference. But this part, it's the part with Hg2 plus, no problem. Hg2 plus here could be in equilibrium with HgOH2. So that means only this part makes sense. Again, it's a little bit of practice, but it's very logical. You see that in the next example, and then at least 2 examples in the problem set and the problem solving lecture, and 1 in the exam. So, but it could be very easy if you practice, which is again very logical. So now we did that thermodynamically impossible scenario by trimming the lines, and now we have 3 distinguished regions in this graph. Forget about all the lines, just focus on the blue line. Based on the blue line, this would be the region 1, this would be region 2, and then this would be region 3. 2 more lines are missing, which is related to water, again, because I think we're not in the range here, but we're going to include that in the next example. But we always have those 2 lines. So now, what's the dominant species here? We had 3 species, and then we have 3 zones. What is the dominant species here? Exactly. So it's checking all the boxes. So this is Hg2 plus. What's this guy? Yep, Hg liquid. It has to satisfy all the lines. So that means 1 line is telling me Hg is here. So that be. So that means Hg is in equilibrium. Oh, sorry, let's do the last part. And then obviously this one would be HgOH2. And now tracing the lines, this would be the equilibrium between Hg and HgOH. This would be the equilibrium between Hg and Hg2 plus. Okay. So let's say you have in your system Hg2 plus, and it's a toxic material, let's say. Then your option to remove it from the environment as Hg2 plus is either to go this way, increase the pH, or to go this way to reduce the electron activity, or to increase the electron activity, to remove it as either the liquid or a complex. So again, it doesn't tell me what's the concentration of Hg in this region. It tells me this is the dominant species. So let's say if you're in an environment that is limited by pH of 7, so you cannot go below pH 7, and then your starting point of pH PE is here. So that means you can't go from Hg liquid to Hg2 plus. The only option is going back, basically backward, going up. Again, if you're here, it would be easy. So that's sort of analogy of you have 2 options to play with to get to the desired product. So again, this is a very, very useful figure. And you see it, I'm sure you see it later in other courses as well. Okay, so let's do the last example. This is a little bit more involved in terms of having more lines. Basically, that's that. The same logic. And here we're not going through all the calculations. It's just basically quickly driving the equations, and then mostly looking at how to erase the part of the line that doesn't make sense. So now let's focus on this one. So it's a system with carbonate or carbon, H2CO3, carbonic acid, bicarbonate, carbonate. Obviously, these are from a pKa1, pKa2. So even without doing the calculation for oxidation state, we know this is a part of an acid base. But this guy, the oxidation state is different, methane. So that means it's different than this one, different than this one, and different than this one. So how many equations of the line we're expecting? How many? 4. So 1 acid base, 2 acid base, 3 redox, 4 redox, and 5 redox. So 3 redox, 2 acid base. So we're expecting 5 then. So the first one is basically H2CO3 going to H bicarbonate plus proton. And then this would be pH would be equal to pKa1 or 6.3. That's the first one. The second one would be bicarbonate and carbonate. CO3 plus H plus. And then pH would be pKa2, 10.3. The third is basically the methane. Rate carbonic acid. The equation would be PE equal to 2.71 minus pH. And the next one is between methane and bicarbonate. Then the equation would be PE 3.50 minus 9/8 pH. And then the last one is basically between methane and carbonate. P 4.79 minus 5/4 of B. So now we have the equation of the line. The next step would be basically drawing the lines. It would be a simple task in Excel or even by hand if you have the graph. But the good news is we already have it. And it shows each line represent what exact reaction. Also, we have water oxidation and reduction lines. So every line that is beyond this box is thermodynamically not feasible. So this part, like this part, it doesn't make sense. This part doesn't happen, and these two. So that's basically, it narrows down between the water splitting window again. So looking at the lines, we know that this is basically all the vertical lines are for acid base. So that's what we talked about. The first one is the first pKa of bicarbonic acid bicarbonate. So this one. And this one is for bicarbonate carbonate. So this line, considering this line, what is on the left and what is on the right? What's on the left of this one? Exactly, so H2CO3. And obviously this one is HCO3 minus. This one is opposite, HCO3 minus going to CO3 2 minus. We don't have any horizontal line because we don't have a simple redox reaction. All the other 3 redox reactions are related to methane with either of these species, either carbonic acid, bicarbonate, or carbonate. So these 3 lines are representing the equilibrium between methane and one of these species. And you have the caption, then you see that. So in all of this line, is methane in the bottom or on the top? Which one is it? Why on the top? So on the top, P is less. E is less, sorry. P is, so low electron here, high electron here. So that means when you have high electron, then the reaction is pushing this way, forming methane. So methane in the bottom part of this line. So we have always methane in the bottom, and then on the top part, this would be either one of these three species. So let's go a little bit unconventional with cutting these lines. So this line is telling me everything on this part has to involve only carbonic acid. There shouldn't be any carbonic, bicarbonate, or carbonate. And we know this is methane and one of these species. So in this part, only methane with bicarbonate, with carbonic acid makes sense, right? So which line is that in terms of the color? It's gray, yeah. So only the gray part makes sense. So now in the middle part, the middle chamber, it's the bicarbonate territory. So only bicarbonate with methane would make sense. Which line is that? Yellow, yeah. And similarly, this is basically the part that only carbonate and methane makes sense, which is basically the red one, right? So it looks like they have the same slope, but these three have different slopes. And when you look at the equations in the previous page, you see that the slope is, one of them is 9 minus 1, minus 9 divided by 8, and minus 5 divided by 4. So slightly different. So in the bottom, obviously we have methane. This is the methane zone, and again, that water oxidation reduction is basically the boundary for the species. So now let's cut this line. What part makes sense? This part obviously doesn't make sense. How about this part? It's the methane region. This line is representing bicarbonic acid and bicarbonate, so it's irrelevant. And this part obviously is beyond that window. So only the middle part makes sense. With the same logic, we can also work on this one and say this is the only part that makes sense. So what are the regions then? From the left? Exactly. HCO3 minus. And obviously this line is also the boundaries of what is here. What's that? Oxygen. Yep. Right from the very first equation we have. So, and obviously the bottom part is hydrogen. So it's dividing the whole region into 1, 2, 3, 4, 5, 6 dominant, 6 different zones. In each zone, one species is dominant. So if you want to go between carbonic, bicarbonate, and carbonic acid, you just need to change the pH. You can't go between the two by changing the electron activity, right? Because if you go change the electron activity, go up or down. If you reduce the electron activity, eventually water is splitting in terms of producing oxygen. If you reduce carbonic acid, you first form methane, but if you keep going, you form water. Hydrogen, and so on. So again, this is a very useful kind of information. It doesn't give us the exact concentration, but rather it gives us the region with dominant species. And you see more and more of this in the more examples that you have. In general, acid-base or complexation kind of reaction, this would be a pure redox, and this line would be a redox that also involves proton. That means pH-dependent redox. So to wrap up what we talked about some equations for the line. We had a procedure how to construct the pe-pH, specifically how to erase the part of the line that doesn't make sense, and interpret some of the information of what is the dominant species. So the minor difference between what we had in the previous part, which was basically a pH or PE, was that we had the exact concentration, but now in the PE, and this was for a given pH, but now for pe-pH, we have basically a line and some sort of dominant zones that it gives us the information about what is the dominant species there. And as mentioned, the next lecture would be on the problem solving for chapter 3 and 4.